Right, I'm coming on now to differential equations, which section 5c. And in this section, we're still dealing with homogeneous linear equations with constant coefficients. Only in this particular case, we're going to be concentrating on when the complex roots to the auxiliary equation arise. So I'm going to do two examples. Firstly, find the general solution to the differential equation d2y dx squared plus 6dy dx plus 13y equals 0. So the auxiliary equation will be m squared plus 6m plus 13 equals 0. And by use of the quadratic equation formula, we'll quite easily obtain the two roots. M1 equals minus 3 plus 2i, and M2 equals minus 3 minus 2i. These equations, roots will always appear in conjugate pairs if the coefficients are real numbers. Now, the solution, as we did before, will be y equals e to the power of the first m times x plus b times e raised to the power of the second m times x. So in this case, it will have y equals ae to the power minus 3 plus 2i x plus be to the power minus 3 minus 2i x. So we've got that far. And I've just taken out the common factor e to the minus 3x to tidy things up a little. And what's left behind inside the bracket will be ae to the power 2ix plus be to the power minus 2ix. Now I'm going to use a well-known result, which most of you will be familiar with, I hope. And it goes like this, that e to the power ikx is cos kx plus I sine kx, and similarly, which is really the same formula, with x replacing minus x replacing x, which will give us e to the minus kx equals cos kx plus I sine kx. These results are attributed to a certain Dr. Euler, okay, who made massive contributions to the subject of mathematics. Now, this solution then transforms to using the formula above to y equals e to the minus 3x bracket a cos 2x plus ai sine 2x plus b cos 2x minus bi sine 2x. So next line, y equals e to the minus 3x bracket. I've collected the cos x's together and the sine x's together to give us a plus b cos 2x plus I times a minus b sine 2x. So we're down to here. Now, these two quantities associated with the cos 2x and the sine 2x are both constants. They're not dependent on x at all, so we can replace them with constants p and q to get the final result. Y equals e to the minus 3x times p cos 2x plus q sine 2x. This is known as damped harmonic motion, I think. If I'm wrong, I'm sure someone will correct me. Okay, but that's not the important part. So we move on to the next example, and this time we'll have a third order differential equation. So here it goes. Example 2, find the general solution to the differential equation d3y dx cubed plus 8d2y dx squared plus 45y dy dx plus 116y equals 0. So we're down to there. Now the auxiliary equation will then be m cubed plus 8m squared plus 45m plus 116. So we're down to here. You can, using the factor theorem, by trial and error, find that minus 4 is a root of that equation. And so factorizing that, we'll get m plus 4 into m squared plus 4m plus 29 equals 0. The second equation will have complex roots. And the roots for the complex part can be found using the quadratic equation formula as before. So the roots will turn out to be minus 4, minus 2 plus 5i, and minus 2 minus 5i. And the solution, as before, will be y equals ae to the 4x, and then the complex part plus be to the power minus 2 plus 5i x plus ce to the minus 2 minus 5i x. So we're down to here. Again, taking the common factor e to the minus 2x out, we'll get y equals ae to the minus 4x plus e to the minus 2x plus be to the 5x plus ce to the minus 5x. And using Dr. Euler's formulas, in the same way as we did before, this will come down quite easily to y equals ae to the minus 4x plus e to the minus 2x, p cos 5x plus q sine 5x. And that completes it. I've put down a couple of examples for you to practice with, and I should do them exactly in the way that I've done the two illustrations, because that is just about as short a method as you can get. When you've had practice with these and you get the equations, the roots for the auxiliary equation, you might be able to quickly, rapidly write down the general solution straight away. That's done with just a little bit of practice. Now, here are the two illustrations which I've written down. I won't read them out. I'll just leave them on the screen for a couple of minutes so you can take a note of them if you wish to.